I'm going to present you how to witness Wigner negativity. This is a joint work with Ulysse Chabaud and Frédéric Grosshans. First, what is a Wigner function? We work in the continuous variable formalism. The Hilbert space is thus infinite dimensional, and for instance, it comes with a countable orthonormal basis known as the Fock basis, which is also known as the photon number states. In this formalism, quantum states can be equivalently represented in phase space with, for instance, the Wigner function. Here are represented a Wigner function for the first Fock states in the position momentum space. And you see that the only Fock state which has a non-negative Wigner function is a vacuum state, k at 0, and all of the states, and even for larger Fock states, they all have a negative Wigner function. So the Wigner function is a quasi-polarity distribution. It sums to 1, but it may have negative values. And these negative values are kind of feature of non-classicality. Also, one straightforward operation you can do on phase space is just a displacement operator with just displacing your Wigner function in phase space. Okay? Now, why would we study Wigner negativity? The first motivation is due to Mary and Isaac back in 2012, which gave a generalization of the Boltzmann-Neal theorem. Basically, if your whole computation can be represented by a positive Wigner function, then it can be efficiently classically simulated. So Wigner negativity is a necessary condition for quantum speed. Also, due to Mark Howard, there is a link between contextuality and Wigner negativity in discrete variables, and we are currently trying to extend this link to the CV realm. Another motivation is that while it's quite easy to characterize Wigner non-negative pure states, because due to Athens theorems they correspond to Gaussian states, it's not the case for mixed states, and it's quite hard to characterize non-negative Wigner non-negative mixed states in CV. So the main question we'll address is the following. Can we get an experimentally accessible witness for Wigner negativity? The basic idea is the following. How do you check that your Wigner function is negative? Well, the first thing you can think of is just to fully reconstruct the density matrix by tomography, but it's very costly in terms of samples that you need to reconstruct it. So another idea is to go with witnesses. Basically, you have in yellow your convex set of Wigner positive states, non-negative states. And what you want is an observable omega together with a threshold value little omega, such that it gives a witness of Wigner negativity. So if your expectation value with any quantum state with your witness is greater than little omega, then you're certified that your state is Wigner negative because you're in this blue region. Note that if you're less than little omega, then you can only say that your witness won't be able to detect Wigner negativity because your state may be Wigner positive or Wigner negative. Okay, so now what's this family of witnesses? We'll take, for the family of witnesses, finite sum of displaced Fock states. So it's just a sum of Fock states which you displaced, and you put some weights in front of any all Fock states, which gives the witnesses. Now the expectation value with any quantum state is just given by the fidelity with your displaced state with a Fock state. So it's quite easy to implement experimentally. And note that you can also just forget the displacement if you take homodyne or heterodyne detection and just compute them via classical post-processing. So you can basically get rid of the displacement. And remember that together with a witness big omega, you have to compute a value little omega, which gives the hyperplane, if you want, in the picture I showed earlier. And so the computation of little omega is as followed. You try to maximize the expectation value with any quantum states, such that this quantum state is Wigner positive. And note that we don't have the dependence on the displacement alpha, because Fock states are rotation invariants. So you can also get rid of this displacement operator. And so now the question we'll try to address is, okay, so this is like beautiful in theory, but how do we actually compute these threshold values little omega? And that may be pretty hard, because you see here that it depends on an optimization of quantum state with a positive Wigner function. So this may be like quite hard in general, right? But before that, a nice feature of our family of witnesses is that it forms a complete family of witnesses, in the sense that if you take any quantum state which has a negative Wigner function, then you're certified that there exists at least one witness which will detect it. Here I presented single-mode witnesses, but you can easily extend them to multi-mode with just multi-index notation, so that's quite nice. These witnesses are rather easy to measure experimentally, and the threshold value little omega can be well estimated, and we'll see that in a second. But first, an interesting observation is that the amount by which you violate the threshold value little omega gives an upper bound, a lower bound, sorry, on the distance to the Wigner positive states. So if you violate the witness, the amount by which you violate the witness is a lower bound to the distance to the set of Wigner positive states. So this gives an operational link to the violation of our witnesses. But now, the main question, how do we actually compute the threshold value associated to these witnesses? So first, to make it more simple, we try to focus on witnesses with a single Fock state. So just the witness associated to NN. Okay, and you can just easily generalize the result which will follow just by linearity if you want. So what we want to compute is this, the fidelity with the Fock state A with a quantum state rho which is Wigner positive. And now the nice thing is that if you apply a random dephasing to the state you have to optimize over, rho, then it won't change the fidelity with any Fock state, because Fock states are phase invariant, they're rotation invariant. But rho then changing to a mixture of Fock states, so you lose off-diagonal terms in the Fock basis, so it's much more easier to characterize. And it won't increase Wigner negativity. Wigner negativity is a monotone with respect to random dephasing. And so basically you can restrict the search to mixture of Fock states to detect Wigner negativity with our witnesses. And we'll see that follows computable programs for computing this the value little omega. And it's actually a linear program, so you can express this as this linear program. So you see that you're looking for, so you express, rho as a mixture of Fock states, which is diagonal in the Fock basis. So that's why you're looking for a family of Fk, and you try to maximize the nth term, Fn, which corresponds to the expectation value n rho n. Then you have a normalization condition. You require that all Fk's are positive. And then you want your Wigner function associated to rho. So by linearity, this becomes the Wigner function, the sum of Wigner function on Wk, which is the Wigner function of Fock state k, to be positive. Okay? So Wk is this. So you see that you have an exponential which doesn't depend on k and only depends on the amplitude of alpha, and you have the case Laguerre polynomial which also depends only on the amplitude of alpha. So basically you can replace this constraint, which is a constraint on all c, by a constraint on r plus, because it only depends on the amplitude of alpha. Okay, and so this is your program, but your program has a problem, right? So it's a linear program, but you're looking for an infinite family of Fk, and you also have a constraint on all R plus. So basically it's an infinite dimensional linear program. So basically, and you can't compute that you can run that on a computer, right? Now, how to actually compute these witnesses? Well, there are like known techniques for making this infinite linear program actually computable on a computer, runnable on a computer. First one is by relaxation. If you eliminate some constraints, for instance, then you will optimize on the outside of the feasible set of solutions originally, and maybe your program will be much easier if you do so. Another solution is to go by restriction. So for instance, if you impose a form of your solution or if you add some constraints, then you will optimize from the inside of your set of feasible solution originally. And the idea is that with clever relaxation and restriction, maybe you can transform your infinite linear program into finite dimensional semi-definite programs. And you can run actually semi-definite programs on a classical computer, and it will be solved efficiently. So you have algorithms that solve them efficiently. Here is the main result of the paper. LPN is the infinite dimensional linear program that computes the threshold value omega n. And if you remember, this is an optimization problem of a positive continuous function. You can express its dual, which would be an optimization over positive measures. And LPN is a maximization program. And now, if you want to approximate this problem, you have two possibilities: relaxation or restriction. If you want to relax this problem, one possibility is, instead of requiring that your function is positive on R+, you require that this function has a positive inner product with polynomials of increasing degrees. More technically, it's polynomials times a decreasing exponential. And this will give you a hierarchy of SDPs. And now if you want to show that this actually converges to this value, well, you have to remember that first, these values necessarily upper bounds this one for all rank in the hierarchy, because this is a relaxation. And now what you do is you show that this set, the feasible set here, is non-empty and bounded. You extract a limit for all programs in the sequence, and you show that this limit by diagonal extraction is actually feasible for this program. And because it's feasible and this is a maximization problem, then necessarily this value converges to omega n. And you can do the same for the restriction. So how do you obtain the restriction? Well, instead of requiring that you have a positive function, you require that you have a polynomial of fixed degree that is positive, and the degree of the polynomial fixes the rank in the hierarchy. Okay? And then you can do the same to extract a solution here that is feasible for LPN. But note that this is quite subtle, like you have a problem here, because I won't enter into the detail, but like the sequence you extract may not be feasible for these programs here, so you have to be quite subtle and you have to introduce other spaces, but in the end it works out and the two hierarchies converges to the value here. So you have a hierarchy of upper bounds and a hierarchy of lower bounds. So now, how to use this hierarchy of SDPs? A procedure to witness Wigner negativity experimentally is, first you choose a Wigner negativity witness, and in the paper we have a discussion on the heuristic to choose a good witness. Then once you choose this witness, you run the hierarchies of SDPs to get upper and lower bound at a given rank, and you try to have the rank that is higher as possible. Once you have these values at upper bounds and lower bounds, the threshold value, you get an experimental estimate for the expectation value with your quantum state, and now you compare. If your expectation value is greater than the upper bound, then your state is Wigner negative somewhere, and if it's less than the lower bound, then your witness cannot detect Wigner negativity, but you cannot conclude if your state is Wigner positive or Wigner negative. Okay? And now these are some examples of applications. So we computed the values for witnesses expressed as single Fock states for n going from 1 to 10, and these are the values represented here. And now one possibility is that if you want to test that your state is Wigner negative, then what you can do is compute, for instance, the fidelity with Fock state 4, and if you find that it's greater, say, than 0.45, then the expectation value, then you will say that your state is indeed Wigner negative. Another example of application is if we go to multimod, because I said that all the results in the paper are generalized, you can generalize them to multimod. And so what we computed here is the detection of the negativity for a low C state, a low C 1-1 state, okay? And so the appropriate witness is actually 1-1, okay? And so we computed the range for which we can detect Wigner negativity, the range of loss for which we can detect Wigner negativity. And you see, for instance, that up to this value, you can detect Wigner negativity because you have a fidelity that is greater than the bound, the threshold value. Okay. Okay, and so with that, I will conclude. So the take-home message is that we constructed a family of witnesses that is complete. So we can always detect a state that is Wigner negative if you pick the right witness. We have an extension to the multimode setting. These witnesses, the expectation value with these witnesses can be efficiently estimated experimentally even in the multimode setting if with an approximation. The violation by which we violate the bound gives us a lower bound to the set of states with positive Wigner function, so it gives us an operational meaning to this violation. And the threshold value can be computed with two hierarchies of converging semi-definite programs to get either an upper bound or a lower bound. And so if you go high enough in the hierarchy, you will get a good estimate for your threshold value. And we also provide the codes necessary to implement the hierarchies, so you can find them here if you want to play around and start witnessing either numerically or even experimentally Wigner negativity. And with that, I would thank the organizer of QPL 2021 and yourself for your attention.